Hello, friends. A warm welcome to Next Page Wisdom. Today, we are going to talk about The Structure of Scientific Revolutions by Thomas Kuhn. Have you ever thought that the science we study in schools and colleges has not always been the way it is now? The truth as we know it is not carved in stone, but keeps changing with time. We often think of science as moving forward in a straight line, where every day we just add new information to the old, like placing bricks in a wall. But what if I told you that science doesn't work like that? What if the development of science doesn't happen in a straight line, but through massive shocks, like an earthquake, where the entire old building collapses and a completely new structure is built in its place? This is exactly what Thomas Kuhn explains in his revolutionary book. He gives us a completely new perspective to look at the truth of science. This audiobook is going to be a bit long because it contains very deep ideas. That's why I would request you to share or save this video beforehand, so you can listen to it comfortably, taking breaks in between, and absorb every idea into your life. So let's go on this exciting journey together and find out how scientific revolutions happen and how they change our world and our way of thinking forever. Chapter 1. What is normal science? The everyday puzzles of science. So friends, let's begin this journey with the world of science that we all know the most about, but perhaps understand the least. Thomas Kuhn calls this world normal science. When we think of a scientist, an image often comes to mind of a person sitting in a lab, discovering something new, something that will change the world. But Kuhn says that most of the time, most scientists are not doing anything revolutionary. Instead, they are solving puzzles. Now you might be wondering, what does puzzle solving mean? To understand this, let's take a very simple example. Suppose you have a jigsaw puzzle with 1,000 pieces. You know that once all the pieces are placed correctly, a beautiful picture will be formed. You can even see that picture printed on the box cover. Your job is not to change the world. Your job is not to change that picture. Your job is only to put the scattered pieces in their right places to complete the picture. So, normal science works in exactly the same way. The scientific community has already agreed on a picture, a framework of how the world works. This is what Kuhn later calls a paradigm, which we will discuss in detail in the next chapter. For now, just understand that scientists already have a map, and their work is to make that map clearer and more detailed. In the period of normal science, scientists do not ask fundamental questions. They don't ask whether the law of gravity is wrong or whether the speed of light can change. No, they accept these principles as true and work within them. They simply try to see how these principles apply to the small details of nature. For example, an astronomer won't ask whether planets revolve around the sun. Instead, using the established rules, he will try to calculate the exact orbit of a newly discovered small planet. A chemist won't question whether atoms really exist. He will simply see what happens when two different chemicals are combined, according to the already established rules. So, in a way, normal science is very safe and stable work. There is very little room for failure because the rules are already set and the destination is already known. If an experiment doesn't succeed, it is not considered proof that the theory is wrong. Instead, it is assumed that the scientist must have made some mistake in carrying out the experiment. The error could be in the instruments or in the calculations, but never in the basic framework or theory that everyone trusts. It is like a game in which everyone knows the rules and everyone follows them. Thought. Now the question arises, if normal science doesn't discover something radically new, then what is its benefit? Its benefit is enormous. This is the phase when science makes rapid and deep progress, because thousands of scientists are working in the same direction, using the same framework. Together, they fill in even the smallest details of that map. They succeed in understanding nature's mysteries at a much deeper level. Think about it. If every scientist woke up every morning doubting whether Newton's laws were correct, no one would ever be able to make the precise calculations needed to send a rocket to the moon using those very laws. Normal science gives us the strong rules on which technology and inventions are built. It is the hard, everyday work that makes science reliable and useful. This is the phase when knowledge accumulates, like a pot filling up drop by drop. Scientists improve their instruments, make their calculations more precise, and strengthen their understanding of nature. Attend. This process creates confidence, a sense of trust that we understand the world and that the rules we have are indeed true. But friends, here the story takes an interesting twist. When you keep solving the same puzzle very carefully and for a very long time, what happens? Your eyes become sharper. You begin to notice even the tiniest details that others might miss. And sometimes, while solving the puzzle, you come across a piece that simply does not fit anywhere. You try placing it in every possible spot, but it just doesn't belong to that picture. At first you ignore it. You think maybe the piece itself is defective, or maybe you made a mistake. Scientists behave in exactly the same way. When an experiment produces results that were not expected, results that go against the established theories, they treat it as an inconsistency, an anomaly, and set it aside. They assume perhaps the instrument was faulty or there was some mistake in the calculations. They label that strange result as an exception and move on, hoping that a simple explanation will appear later. They do not want to question the beautiful picture, the reliable framework that has taken generations of hard work to build. This is the most important paradox of normal science. On one hand, its purpose is to strengthen the existing structure and prove it correct. The entire framework is built on the belief that our current theories are true. But on the other hand, because scientists work so deeply and so precisely, they are also the first to notice the tiny cracks appearing in that structure. They are the first to find puzzle pieces that don't fit anywhere. Normal science is not meant to spark a revolution, but unknowingly it prepares the ground for one. It produces anomalies, raises unsolved questions that eventually become impossible to ignore. It's just like cleaning a spotless white room every day. Your goal is only to keep it clean, but precisely because you clean it so often, your eyes will be the first to notice the small black stain that appears. Normal science is like the daily cleaning of the room of science, and in that very process, it reveals those stains which later cause a great storm. So, normal science is like a calm and steady river that flows slowly, strengthening its banks. But in the very same, within that calm river, forces are also building up that one day will swell into a flood and sweep everything away. These scientists are the diligent craftsmen maintaining a grand building, but they do not realize that their very hard work is revealing the cracks already present in its foundation. So the question is, what happens to that one puzzle piece which doesn't fit anywhere? What happens when more such pieces begin to appear? What happens when scientists can no longer ignore those strange results? Here the story reaches a new and exciting twist. But to understand that twist, we first need to understand the map or picture that all scientists put their trust in. What exactly is it? What name does Kuhn give it? And why is it so powerful that scientists even try to deny the truths that go against it? We will find the answers to all these questions in the next chapter. Chapter 2. The Power of Paradigms. The Invisible Rules that Drive Science. Friends, in the previous chapter, we explored the world of normal science, where scientists solve puzzles within already established rules. We talked about the map or picture that all scientists accept as true. Now it's time to learn about that mysterious and powerful thing that Thomas Kuhn calls a paradigm. A paradigm is not just a theory or a set of principles. It is much more than that. It is an entire worldview, a lens through which the whole scientific community works. Without this lens, they cannot see anything at all. A paradigm includes not only scientific theories, but also decisions about which questions are worth asking, which methods are acceptable for finding answers, and which instruments should be used. It is like an unwritten rule book, passed down from one generation of scientists to the next. When a student begins to study science, they are not just taught Newton's laws or Darwin's theory. They are taught to think within that paradigm. They are trained to think like a scientist. Let's understand this with another example. For centuries, the paradigm of Aristotle and Ptolemy ruled the world. According to this paradigm, the Earth was the center of the universe, and the sun, moon, and planets all revolved around it. This was not just an astronomical theory. It was an entire worldview. It was tied to religion, philosophy, and even to people's everyday thinking. Within this paradigm, a good astronomer was one who could explain the motion of the planets while keeping the Earth fixed at the center. If someone asked whether the Earth might actually revolve around the Sun, that question was considered foolish and unscientific. It was a question outside the paradigm. At that time, scientists invested all their energy and intelligence into trying to explain the strange motions of the planets while still keeping Earth in the middle. They even built extremely complex mathematical models for this. They were solving a puzzle whose picture had already been fixed, and that picture was that Earth was the center of the universe. The paradigm told them what to look for and how to look at it. Nas, guys. The real power of a paradigm is that it is invisible. The people working within it don't even realize that they are wearing a particular lens. They believe they are seeing the world exactly as it is. They believe they are directly observing facts. But Kuhn explains that no fact stands on its own. We always see and interpret facts through the lens of a paradigm. For an astronomer working within Ptolemy's paradigm, the rising sun in the morning was a fact proving that the sun revolves around the Earth. For a scientist working within Copernicus's paradigm, the same rising sun was a fact proving that the Earth rotates on its axis. The event was the same, the sun rising, but because the paradigms were different, the meaning of that fact was completely transformed. This is the true power of a paradigm. It doesn't just shape our answers, it also controls our questions. It determines what counts as evidence. It decides what will be considered valid and what will be dismissed as mere noise. It is a kind of mental prison, but the prisoners don't even realize they are imprisoned. They think they are free and that they are seeing the world exactly as it is. Dad, I want to ask you, can you identify any such paradigm in your own life or in your society, a belief or mindset that everyone takes as true and never questions? Share your thoughts in the comments. A paradigm helps scientists work together in one direction. Since everyone is following the same rulebook, they can easily understand each other's work, trust one another's results, and make rapid progress together. It is like a shared language and a common goal. Without it, science would be scattered and chaotic, with everyone playing their own tune. A paradigm makes science disciplined and organized. It also provides a framework for training young scientists. Textbooks, which we treat as sources of knowledge, are actually the most important tools for instilling the existing paradigm in students' minds. They present the history of science as if it has always advanced in a straight line, and as if the current paradigm is the final truth. They throw all those revolutions, debates, and defeated paradigms into the dustbin of history so that students' faith in the present system remains intact. They tell a neat, tidy story, while the real history of science is full of upheavals and struggles. Yet, every coin has another side. The greatest strength of a paradigm also becomes its greatest weakness. Because it trains scientists to look in one particular direction, it blinds them to all the other directions. Scientists cannot even see the things that don't fit their paradigm. Right. If any evidence appears that challenges the paradigm, their first reaction is to reject it. They say the experiment must have been faulty, or it's just an exception. They don't question the lens itself. Instead, they question whatever doesn't look right through that lens. This is a kind of psychological defense mechanism. No one wants to abandon their entire world, their entire understanding in a single blow, especially when they have spent their whole life building that understanding. That's why a paradigm fiercely resists change. It wants to preserve the status quo. It can go to any extent to protect itself, like a powerful empire that crushes any rebellion before it even begins. So we have seen that a paradigm is like a double-edged sword. On one hand, it makes normal science possible, allowing science to go deeper. It unites scientists into a community and gives them the power to work together. On the other hand, it limits thought, suppresses new and revolutionary ideas, and blinds scientists to facts that could shake their worldview. Enes. It is like a comfortable and safe house, but with walls so strong that no news of the outside world can get in. It is that invisible force which decides what is true and false, what is possible and impossible. But friends, as we discussed at the end of the last chapter, what happens when that one puzzle piece that doesn't fit can no longer be ignored? What happens when such pieces keep appearing again and again? What happens when cracks begin to appear in the strong walls of the house and the outside air starts to come in? When a paradigm that once seemed so powerful and stable begins to falter, what happens then? Say, that period is what Kuhn describes next. And it is this period that gives rise to the most dramatic and exciting moments in the history of science, a time of crisis that either destroys everything or gives birth to an entirely new world. It will give birth to something new. We will learn about that story of crisis in the next chapter. Chapter 3. When rules begin to break. The era of anomalies and crisis. Friends, in the previous chapter, we understood the powerful world of paradigms, which is like a safe fortress for scientists. It gives them rules, direction, and a lens to recognize truth. But history bears witness that no fortress remains impenetrable forever. Sooner or later, cracks begin to appear somewhere. In the world of science, Thomas Kuhn calls these cracks anomalies. An anomaly is the puzzle piece that doesn't fit anywhere. It is the experimental result that doesn't match the predictions of the current paradigm. It is that strange noise that suddenly starts coming from an otherwise perfectly running machine. At first, as we discussed, scientists tend to ignore it. This is human nature. If your favorite vehicle, which has been running flawlessly for years, makes a slight unusual noise one day, you don't immediately assume the engine has failed. You think maybe the road was rough, or perhaps you just misheard. Scientists do the same. They blame their instruments, recheck their calculations, or dismiss the anomalous result as a rare exception and continue their research. They don't want to doubt their beloved paradigm, their beautiful picture of the world. But what happens when that strange noise keeps coming back? When the anomaly is repeated again and again in different laboratories by different scientists? Then it becomes hard to ignore. It is no longer just an exception, but a direct challenge to the rules of the paradigm. That is where the period of crisis begins. A crisis is the time when the scientific community's trust in its paradigm begins to waver. The rules, which once seemed carved in stone, now appear weak and incomplete. Puzzles that were once easily solvable suddenly become more difficult. Unease and insecurity spread among scientists. A classic example of this is the period before Copernicus's revolution. Ptolemy's paradigm, the geocentric universe, had worked for centuries. But as astronomers began observing planetary motions with better instruments, their calculations and predictions stopped matching accurately. Planets sometimes appeared to move forward, sometimes backward. To explain this anomaly, scientists kept adding more complexity to Ptolemy's model. They introduced ideas like epicycles, planets moving in small circles while also moving in larger circles. Gradually, the model became so complicated and clumsy that it was hard to believe in. It looked like a machine patched together with thousands of fixes. Every attempt to correct the anomalies only made the model more tangled. In times of crisis, the very nature of science changes. Normal science, which was about solving puzzles, turns into open debate. Scientists are no longer just solving puzzles, but questioning the very rules of the game. Questions that were once dismissed as unscientific or purely philosophical now become the subject of serious discussion. Young and new scientists, who have less invested in the old paradigm, become bolder and more rebellious. They start presenting new ideas that may sound strange or absurd. A kind of intellectual chaos spreads. Everyone recognizes the problem, but no one has the solution. Established scientists use all their strength to defend the old paradigm. They insist, we just need to work harder, make more precise calculations, and everything will be fine. But deep inside, their confidence is already hollowed out. This is a very tense and uneasy time. The scientific community is losing its most valuable asset, its shared belief. Another striking feature of this period of crisis is that the anomaly, the root cause of the crisis, is often not some brand new discovery. It is usually something Sometimes these issues are known to scientists for decades or even centuries, but they are ignored at first. For example, the problem with Uranus's orbit could not be explained by Newton's laws. Scientists had known this for a long time, but as long as Newton's paradigm remained firmly in place, it was treated as just a minor unsolved puzzle and set aside. But when, toward the end of the 19th century, more anomalies began to appear, such as the behavior of light, the old anomaly of Uranus's orbit suddenly became far more significant. In times of crisis, old forgotten problems come back to life and drive nails into the coffin of the old paradigm. It is exactly like a relationship in which, once cracks appear, old small grievances suddenly begin to feel very serious. Crisis changes the way we see things. What once seemed unimportant now appears as the system's central flaw. The crisis stage is essential for science. It is the time that opens doors to new ideas. As long as the old house stands strong, no one thinks of building a new one. But when the old house becomes dilapidated and its roof starts leaking, only then do people begin to think of designing a new house. Crisis forces scientists to think outside the box in which they were imprisoned. It pushes them to question those basic assumptions they had accepted, without ever really examining. It is like waking the paradigm from its sleep. It shows that nature cannot always be confined within the little boxes we construct. Sometimes, we have to change the boxes themselves. But creating a new paradigm is no easy task. It is not just about making some improvements to the old one. It is like seeing the entire world from a completely new perspective. It requires imagination, courage, and an entirely fresh way of thinking. And the period of crisis is like a dark night. The old moon has set, but the new sun has not yet risen. Everywhere there is uncertainty and confusion. Scientists feel as if the ground beneath their feet has shifted. The old map is useless, and the new map has not yet been drawn. So, friends, we now arrive at the most dramatic turning point in the story. The old paradigm is breathing its last. The burden of anomalies has become unbearable. The scientific community is in deep crisis. Everyone is searching for an answer, searching for a new path. The atmosphere is filled with tension, hope, and restlessness. At such a time, how does the birth of a new idea happen, one that changes everything? Who is it that brings forth an entirely new map? And when that new idea emerges, does the old paradigm give up easily? Or does it spark one of the greatest intellectual battles in history, a struggle involving not only logic and evidence, but also emotions, politics, and clashes between generations? The story of this great battle is the story of the birth of a scientific revolution. We will learn about this in the next chapter. Chapter 4. The Birth of a Scientific Revolution. The Death of the Old Truth and the Beginning of the New. After the dark and uncertain phase of crisis, we now enter the moment when the first rays of a new dawn appear. This is the moment that Thomas Kuhn calls a scientific revolution or paradigm shift. Friends, this is the most dramatic, the most violent, and the most transformative moment in the history of science. It is not a peaceful transition where old scientists kindly hand over power to new ones. No, it is a true revolution, a struggle in which one worldview uproots and overthrows another. A scientific revolution happens when, during the period of crisis, one or a few scientists propose an entirely new paradigm. This new paradigm not only explains the old anomalies, but also offers a completely new way of looking at the entire world. It is not a small adjustment to the rules of the game. It changes the whole game itself. The most prominent example of this is the Copernican revolution in astronomy. When Ptolemy's Earth-centered model was in crisis, Copernicus proposed a revolutionary idea. What if we remove the Earth from the center and place the sun there instead? This idea was not just a mathematical adjustment. It was an earthquake that shook the foundations of centuries-old beliefs. Suddenly, everything about the universe changed. The Earth, which had been seen as fixed and central, was now just another planet orbiting the sun like the others. Humans, who had thought of themselves as the center of the cosmos, were now merely inhabitants of a small planet. This one change raised deep questions about religion, philosophy, and humanity's own identity. The new paradigm, the heliocentric model, not only explained planetary motions with greater simplicity and accuracy, but it also generated new questions no one had thought to ask before. For example, if the Earth is spinning, why don't we feel it? If Earth is just a planet, could there be life on other planets too? A revolution doesn't just answer old questions. It opens the path to deeper, more profound questions. Can you think of a moment in your own life when a single idea changed your entire way of seeing the world? Share your experience in the comments. But as I said, such change is never easy. When a new paradigm appears, it is not accepted right away. Most scientists, especially the older generation, who have spent their entire careers working within the old paradigm, fiercely resist it. For them, accepting the new paradigm means admitting that their life's work was wrong. It feels not just like an intellectual defeat, but also an emotional and personal one. That is why a battle begins between the supporters of the old and the new paradigms. Kuhn emphasizes that this battle is not one purely on the basis of logic and evidence, because both sides live in different worlds. Their truths are different, their standards are different, and they cannot even fully understand each other's language. Supporters of the old paradigm look for flaws in the new, while supporters of the new expose the weaknesses of the old. It becomes like a political debate, where both sides promote their own beliefs as correct. Victory in such struggles does not usually come from arguments alone, but from the passing of generations. The physicist Max Planck once said, "A new scientific truth does not triumph by convincing its opponents and making them see the light, but rather because its opponents eventually die, and a new generation grows up that is familiar with it." This is a bitter but profound truth. New paradigms are often embraced by younger scientists. They have less to lose, and their minds are more open to new ideas. Gradually, as the older generation retires or passes away, and the younger generation rises to influential positions, the new paradigm becomes the mainstream. Textbooks are rewritten, and children are taught the new paradigm as though it had always been the truth. The old paradigm, for which people once even gave their lives, is relegated to history as a mistake or a primitive way of thinking. After every revolution, it is the victors who write history. Another important example is the shift from Newtonian physics to Einstein's relativity. For centuries, Newton's paradigm was synonymous with science. His laws seemed to work everywhere. Time and space were considered absolute and fixed. But toward the end of the 19th century, when scientists began studying the speed of light and objects moving at extremely high speeds, Newton's laws began to fail. These anomalies triggered the crisis. Then Einstein came along with a completely new paradigm. He proposed that time and space are not absolute, but change, depending on the observer's motion. Gravity is not a force, but a curvature in space-time. These ideas were so revolutionary that at first, no one believed them. For those who thought in Newton's paradigm, Einstein's ideas sounded absurd, even crazy. But gradually, as experiments confirmed Einstein's theories, younger scientists began to adopt them. And today, Einstein's paradigm is our normal science. We talk about black holes and the Big Bang, none of which would have been possible without Einstein's paradigm. So, a scientific revolution is like dethroning an old king and placing a new one on the throne. Once the new king takes power, he sets new rules, mints his own coins, and rewrites history in his favor. After the revolution, science enters once again into a phase of normal science, but now with new puzzles, new rules, and a new picture of the world. Scientists once again busy themselves with solving puzzles, but now puzzles of a broader, deeper universe. Revolution changes the world forever. It shows us that science is not a collection of fixed facts, but the story of changing perspectives on reality. Truth is not static. It passes through revolutionary transformations. But here, a deep and complex question arises. When one paradigm replaces another, Can we say we are getting closer to truth? Or are we merely replacing one story with another? And can scientists working within old and new paradigms ever truly understand each other? Or are they living in such different worlds that no bridge exists between them? The answer to this difficult and philosophical question lies in another fascinating idea of Kuhn's, which we will explore in our next and final chapter. Chapter 5. A New Way of Seeing the World, the Transformed World, After the Revolution. Friends, in this journey so far, we have seen how science moves through the calm stage of normal science, how anomalies give rise to crisis, and how crisis leads to a revolution that topples the old paradigm. The revolution has taken place. A new king sits on the throne. A new phase of normal science has begun. But what does the world look like after the revolution? Is it just the old world with some improvements? Or is it truly a completely new world? This is where Thomas Kuhn presents his most challenging and perhaps most controversial idea, incommensurability. It sounds like a heavy word, but its meaning is both deep and simple. Two different paradigms cannot be directly compared because they share no common standard of measurement. They are like people speaking two different languages without a translator. Think of it this way. For someone who believes in Aristotle's paradigm, motion means an object's attempt to reach its natural place. A stone falls down because its natural place is earth. Smoke rises because its natural place is the sky. But for someone who believes in Newton's paradigm, motion means a change in an object's state caused by an external force. Both use the word motion, but they mean entirely different things. They are using the same word to talk about two different realities. That is incommensurability. When a follower of Copernicus and a follower of Ptolemy argue, they are not only debating whether the Earth moves or the Sun moves. They are also debating what a planet is, what motion means, and what counts as valid evidence for a good scientific theory. There is no shared foundation for agreement. They can never completely understand each other. Kuhn says that shifting from one paradigm to another is not a logical step where you gradually climb a ladder toward a higher truth. Instead, it is like a religious conversion, a sudden change in which you start seeing the world in a completely new way. This is also called a shift in perspective. You must have seen those pictures where you can either see an old woman or a young lady, but not both at the same time. You have to jump from one perspective to another. A paradigm shift is exactly like that. After a revolution, scientists truly begin working in a different world. For them, not only do the theories about the world change, but the world itself changes. A chemist working before the discovery of oxygen would look at a burning substance and say that a material called phlogiston was being released. A chemist after the revolution would look at the same burning substance and say it was absorbing oxygen from the air. Both are watching the same phenomenon, but their eyes show them two completely different processes. Facts themselves have changed because the paradigm has changed. This idea forces us to question our traditional way of thinking about scientific progress. We usually assume that science always moves closer to the truth. We believe Einstein was more correct than Newton, and Newton was more correct than Aristotle. Kuhn does not entirely disagree with this, but he interprets it differently. He says science is not moving toward some ultimate, absolute truth. There is no final goal toward which science is heading. Instead, science works more like Darwinian evolution. It does not evolve towards something, but away from something. Each new revolution is simply a better way to resolve the problems and inconsistencies of the previous paradigm. Einstein's paradigm is not better because it is closer to ultimate truth, but because it could solve puzzles Newton's paradigm could not. This is an evolution in problem-solving ability, not a journey toward an absolute truth. This is a humble yet powerful idea. It teaches us not to be arrogant about our current scientific knowledge, because one day another revolution may come that turns our present truths into old stories. So what does all this mean for our everyday lives and thinking? It has deep significance. Kuhn teaches us that each of us lives within our own personal paradigms. These paradigms are shaped by our upbringing, culture, education, and experiences. They are the lenses through which we see the world. Our political views, religious beliefs, and ideas about relationships are all part of our paradigm. And we often forget that we are wearing glasses at all. We assume we are right, and that anyone who disagrees must be foolish or wrong. Kuhn reminds us that maybe the other person is not foolish. They are simply looking at the world from a different paradigm. When we argue, we think we are fighting over facts. But perhaps the real battle is between paradigms. Maybe we are speaking two different languages. Realizing this can make us more empathetic toward others and more humble about our own thinking. It pushes us to ask, are there inconsistencies in my own beliefs? Is there evidence I am ignoring because it does not fit into my paradigm? Experiencing a paradigm shift in our own lives can be very difficult but also very necessary. It helps us move forward and become better human beings. Now that we have completed this revolutionary journey with Thomas Kuhn, let's recall the key lessons this audiobook has given us. Chapter 6. Conclusion. What we can learn from Thomas Kuhn. Lessons of Science for Life. Friends, we have traveled a long and deep intellectual journey. Together with Thomas Kuhn, we have explored a world of science very different from what our schoolbooks show. It is a world where truth is not fixed, where knowledge does not move in a straight line, and where revolutions are not peaceful. So at the end of this audiobook, let's string together the most important pearls we have gathered from this deep ocean. First lesson, normal science and paradigms. We learned that most of the time, science is about puzzle solving within an accepted worldview, a paradigm. This shows us how important shared structure and discipline are for deep progress. But it also warns us of the dangers of being trapped inside that structure. We must always be ready to question our own lenses, whether scientific, social, or personal. Second lesson, the role of anomalies and crisis. Kuhn showed us that progress does not come easily. It comes through strange, troubling facts that don't fit our beliefs. Our instinct is to ignore such things, but real growth begins only when we face these anomalies with courage. Even in personal life, moments of crisis, when nothing seems to work, are often the seeds of our greatest transformation. Crisis forces us to think outside the box in which we were comfortably living. So next time a crisis comes, instead of fearing it, perhaps we can see it as the beginning of a revolution. Third lesson, scientific revolution. We learned that major changes do not happen gradually, but suddenly. A paradigm shift transforms the world forever. Sometimes small adjustments are not enough. We need to change the entire foundation. This shows us the power of bold and radical ideas. Thinkers like Copernicus, Darwin, and Einstein showed us that one person's idea can change the world, if they have the courage to challenge established beliefs. This inspires us to think boldly in our own lives. Fourth and deepest lesson, incommensurability and the nature of progress. Kuhn teaches us humility. He reminds us that we may not be moving toward some ultimate truth. We are simply becoming better problem solvers. This helps us avoid dogmatism. It helps us understand people who think differently are not necessarily wrong, just different. They are seeing the world from another paradigm. This teaches us the value of dialogue and empathy, and it reminds us that today's truth may become tomorrow's myth, just as yesterday's truths are myths today. So friends, the structure of scientific revolutions is not just a book about the philosophy of science. It is a book about ways of thinking. It teaches us how knowledge is created, transformed, and sometimes even abandoned. It teaches us to question our beliefs, embrace change, and respect other perspectives. Thank you very much for joining me on this deep and thought-provoking journey. I hope this audiobook has given you not only a new way to look at science, but perhaps also a new way to look at life. If you enjoyed this audiobook, and if it made you think in new ways, don't forget to like this video. Each like inspires us to create more such knowledge-filled audiobooks. Do share in the comments which of Thomas Kuhn's ideas you found the most surprising or fascinating. Have you ever experienced a paradigm shift in your own life? We'd love to hear your experiences. And yes, if you want to keep exploring such deep and life-changing ideas, Don't forget to subscribe to the Next Page Wisdom channel and press the bell icon so you don't miss any of our upcoming audiobooks. Once again, thank you so much. See you with the next book on a new journey. Until then, keep studying, keep learning, and keep thinking.